Welcome everybody to parallel session Nanomaterials 3. Today we've got two talks, one from Technion by Fariz Khorani, which is already, you can read the title. And the next, in 20 minutes, we will have a talk from Ben-Gurion University by Avia Ohayon Levi, which will talk to us about carbon-loaded polymers, polymer-based composites. So as a reminder, you have 15 minutes of talk and leave, please, 5 minutes for questions. The floor is yours.
Thank you, Lev. So my name is Fares. I'm a PhD student under the supervision of Professor Fatih Lipschitz at Technion. So as you see, today I will present a special topic about 2,6 anisotropic nanocrystals and core-shell colloidal semiconductor nanoplatelets, room temperature synthesis, physical characterization, and exotic optical properties. So as you see, the title is too long and it contains a huge amount of results that will be published soon. But today, due to the short time, I will present just part of these results. So let's begin with an introduction. So first, what is 2,6 materials? So the 2 stands for the last column in the transition metal column, which contains zinc or cadmium, and the 6 is the chalcogen column, which contains sulfur, selenium, and tellurium. So basically, 2,6 materials are in zinc sulfide, zinc selenide, or cadmium sulfide, or cadmium selenide, and these derivatives. So now, how we prepare these materials? So for a typical synthesis of cadmium selenide quantum dots, we use the hot injection method at high temperature. So what we do is we heat the cation in a mixture of solvent and ligand, and we inject the anion. And as you can see here, we have a color change from blue to red. So now, what does that mean, that we have a change from a blue to red? It means that this material is a semiconductor and we have something which is called a quantum size effect. So what is quantum size effect? So in semiconductor, we have an electron in the valence band, and this electron, when it absorbs a photon, it jumps to the conduction band, and then it goes back, it falls back, and when it falls back, it emits a photon, and this photon can have different colors. So basically, changing the color of the quantum dot or the size of the quantum dot can change this band gap, and by this, we can control the light that we see. So now, if I'm gonna ask you a question, which application do you think about for now? So this is TV screens, because in the TV screens, we can have the full range of the colors, and especially when the quantum dots are more stable and more robust than the organic material, it stands for more time and the quantum efficiency is higher. So the quantum dots are used now as in TV screens, and they call it the QLED. The Q stands for quantum dot, and their color is very bright. Other applications for 2,6 materials like tumor targeting, so we can stain tumor and then take them out. We can use them in printing. As you see here, we have different colors of quantum dots, and because they have different colors in the wide range and the visible regime, so we can use them in the smartphones. So now, as we saw in the synthesis, we can prepare different sizes of quantum dots, but this is not the full story. Also, we can prepare different morphologies. So this is how quantum dots look like under a microscope. This is a 3 to 4 nanometer quantum dot. This is the absorption spectrum. And basically, by changing the temperature, changing the concentration, the ligands, we can change the morphology. So here we have a 30 nanometer nanorod because it have a rod shape. And here we have a 2-dimensional nanoplatelet. This is also from 30 to 40 nanometer. And as you see here, we have the absorption spectrum. Now, if we compare the quantum dots to the rods to the nanoplatelets, we can see that each one of these morphologies have a distinctive absorption feature. So for example, if you look carefully in the cadmium selenide nanoplatelets, you can see that the absorption is very sharp. So this is the absorption peak. And if we compare it to the cadmium selenide quantum dot, we can see that the absorption is 2 to 3 times narrower than the cadmium selenide quantum dot. So the nanoplatelets must be one of the most promising materials for now in LED emitting diodes because of their sharp absorption and PL features, and also for TV screens. But researchers found a problem in this material, that they have, as you see, a high a surface to volume ratio. So they can oxidize fast, and they have something called dangling bonds on their surface. So these difficulties in the end created a low quantum efficiency or quantum yield. So what researchers did is they started to build another layer of 2,6 material, okay, above or at the sides. So if we put another layer of 2,6 material above, we call it a core shell. Okay, so here we have a cadmium selenide, and here we can have a cadmium sulfide or zinc sulfide, something similar with the same family. And if we put it on the sides, we call it a core crown. Now, there's a lot of materials that have been created, like core shell or core crown, and these materials have a high quantum yield or quantum efficiency, which can reach up to 98%. You know, researchers like to call it almost 100%. And in this case, we have a better passivation at the surface, and it permits a wave engineering because we can engineer the optical properties based on the materials that we have inside and outside. Now, this is not the full story. So we have so much obstacles and challenges in this field because first, the nanoplatelets have a low thermal stability compared to quantum dots. So as we saw before, we can prepare the quantum dots and the core shell of the quantum dots at high temperatures. But for the nanoplatelets, it's not the same case because they are so much vulnerable to the heating. So it's very hard, but researchers succeed to do this synthesis at a high temperature, but of course, by using a complex synthesis procedure. So they added stabilizers, so much ligand, and this synthesis contains so much steps. The third problem is the strain at the interface. So in the core shell material, we have an interface, and we have two types of material. So because of the mismatch between the two lattices that we have so much pressure on this interface, and at elevated temperature, this pressure is maximized, and it's not good for the quality of the platelets. So as you see here in the TM picture, this is like how the interface looks like under the microscope. And the fourth problem is the scalability, because the synthesis, researchers do the synthesis at high temperature, so it's impossible to scalable these procedures. And from what we saw, these materials are very promising to the industry and to the technologies. So we must find another alternative. So here I came today to give you an alternative. How can we synthesize easy and fast these core shell structures? So today we'll talk about cadmium selenide, cadmium sulfide core shell nanoplatelets, and cadmium sulfide, cadmium zinc sulfur core shell nanoplatelets. Then I will show you how can we manipulate the optical properties even at room temperature. We don't need high temperature to see the color change that we saw before. We can do it at room temperature. And the third thing is the physical characterization. So I will show you also some XRD, Raman, TEM, and HAADF-STEM, so we can get so much information about the physical properties that this material have. And in the end, we have advanced optical measurements like time resolved photoluminescence and lifetime, which I think I will not have time to cover for today, but we'll see. Okay, so first, before preparing the core shell, we want to prepare the core. So how we prepare the core? So we take the cadmium inside the solvent and we put ligands and we heat it until 250, then we inject the selenium. And when we inject the selenium, we saw before that we have a quantum dot, okay? So after 1 minute, we add cadmium acetate, and when we add cadmium acetate, the quantum dots start to attach in a two-dimensional way. So this process is called oriented attachment. So eventually, we have in the final solution quantum dots and nanoplatelets. So now we use centrifugation to select the nanoplatelets over the quantum dots. And in the end, we get cadmium selenide nanoplatelets. You can see that they have a green color. It's very strong. This is the absorption, very sharp. The PL is very narrow. Here is a TEM image of these nanoplatelets. We can see that they are almost 40 nanometer in length, 8.5 nanometer in weight. This is the histogram. And here we can see these nanoplatelets, but this time they are lying on their edge. So, and this is a half stem image. We can measure the thickness, okay, by stretching a line and by scanning the intensity. So after all, the thickness is 1.75, okay, nanometer. And due to the small thickness, the exciton is confined in this regime, okay? And because of this, we have a sharp absorption and PL spectrum. Now, if we want to add,
you have 4.5 minutes left.
Okay. Now, if you want to add a cadmium sulfur shell or zinc sulfur shell at room temperature, what we need is to use molecules that can react at room temperature. So I tried to use thioacetamide and octylamine, an amine molecule. So the amine can attack the thioacetamide to form this complex, and the hydrogen sulfide molecule is released. And then we add cadmium. So the cadmium can react with the sulfur to form a shell around the cadmium selenide, or the zinc can attack the hydrogen sulfide to make a zinc S shell and also to shell the cadmium selenide nanoplatelet. So here these two reactions are explained in root C and root D. So this is the cadmium, this is the acetamide, this is the amine, and this is the nanoplatelet. It's half an hour reaction at room temperature, and we obtain a core shell of cadmium selenide, cadmium sulfur, and the same for the zinc. We obtain cadmium selenide, zinc sulfur. I also did the two control experiment at explained at root A and at root B. I will not explain it, but we tried to make the same reaction without nanoplatelet in order to have a control on this synthesis. So now, what we see from these images, we want to see what we have, what composition what we have. So this is how the cadmium selenide, cadmium sulfur looks like. We have a nanoplatelet shape, and we have spherical particles around. So, and this is the half stem image. So if we scan the elemental mapping, we can see that we have selenium and cadmium inside, but also we have a cadmium and sulfur outside. So basically we stretch a line in half stem and we do elemental EDX mapping. So by this mapping, we concluded that we have this structure as we see here, which is cadmium selenide in green and a cadmium sulfur layer as a shell, and in the surrounding, as you see here, we have a cadmium sulfur dots. So these dots here are cadmium and sulfur. And for the zinc case, it's the same story, except that if you see here the colors that we have, you see that the zinc is not distributed in a homogeneous way. So, and it's very known that zinc is very problematic. So in this case, the zinc is distributed at the edges. So this is the overall shape that we have. We have except instead of having
1 minute left.
Instead of having zinc sulfur shell, we have an alloying shell which contains cadmium, zinc, and sulfur. So now in order to show you the optical properties, so this is the cadmium selenide nanoplatelets, absorption and PL. This is after shelling at room temperature with cadmium sulfur. So we have a shift of 100 nanometer. Okay, so here it's 650. Here it's 550. And when we added zinc, we saw that we have a shift of 50 nanometer, and the absorption and the PL are located in the 600 nanometer. These are the colors that we see, that we obtained. This is the cadmium selenide green. This is with zinc, we have orange, and this is the cadmium sulfur in red. So now the last thing I want to show you is that when we measured the stability, we saw that this is
please move to conclusions. I'm sorry.
Yeah, actually there is no conclusions. So this is the last.
This is the last. Okay.
Yeah. So we saw here that the shelling just increased the quantum yield and the passivation of the surface up to 60 days, and that these two materials, as you see here, are very robust and they stand for 2 months than the cadmium selenide, which vanished so fast. So soon we will publish a paper which contain more data about the time results and the lifetimes, and so stay tuned for the paper. And I want to thank everybody that came, and good luck.
Okay, good talk, good talk. I really enjoyed it. So I have one question. In the previous slide, yes. Why is 60 days your mark?
Actually, I took 1 month, 2 months, 3 months, but I mean, you can take how much one time you want, and then just measure.
I thought that maybe it's some kind of related to the application.
Yeah, actually, I measured this data 2 months ago, so now we are 4 months after this measurement, and it's the same. So I can just replace. Yeah. So it's very, very stable.
You could show maybe several next time, several curves. Moreover, I see Tarek raised his hand.
Yes, I have one question, please. First, thank you for an interesting topic. And in one of your slides, you said, you hear me well? Yeah, okay.
Yes.
You said that the quantum dots are more stable than the organic materials and they are much preferable. Can you explain that, please?
Yes, actually, I have a hidden slide here, which I wanted to explain, but I didn't have time. So this is, for example, a quantum dot, and this is a dye, which is an organic molecule. So as you see here, the quantum dot contains tens of thousands of atoms, and the dye contains just tens of atoms. So any change in the dye, any bond that you break will eventually change the electronic properties and will change the energy levels. So if you see here, so in the dyes, we have a photo bleaching so fast, but in the quantum dot, because of the large number of atoms, it's very photostable.
Okay, yeah. Okay, thank you.
Once again, thank you, Faris. Esti has a question, quick question.
Thank you. It was a very good lecture. I just wanted to ask about the control experiment you mentioned. What did you achieve from this experiments?
Yeah, a good question. So just to remind everybody, so in the control experiment, we did the same experiment. We added a cadmium and a thioacetamide, but without the platelets. So, and actually by changing the metal salt, you can see here that we can obtain a cadmium sulfur nanoparticles, zinc sulfur nanowires, and also another kind of materials like lead sulfur. So the lead is from the 4,6 family. So actually by changing the metal salt and by using thioacetamide, you can also create a quantum dots and different structure at room temperature. So this is the results of the nanocrystals that we obtained without the nanoparticles.
Thank you.
Welcome.
Again, great talk. And now we're going to drum rolls, please. Avia Ochayon Levi, which will talk to us about compression enhanced thermal conductivity of carbon-loaded polymer composites. Good luck.
Thank you. So my name is Aviao Chaim-Lavi, and I'm a PhD student in Ben Gurion University of the Negev, under supervision of Professor Oren Regev. And today I will talk about the compression-enhanced thermal conductivity of carbon-loaded polymer composites. Composite materials are widely used in the industry, mainly in combination with the components that emit heat. Thus, enhancing their thermal properties will be very effective. In my presentation, I will start by explaining the motivation for my research. Then I will explain what composite materials are and their contribution to my research results. So the first question is where we can see the need for heat dissipation in the industry. And the answer is everywhere. It starts with the small components in the electronic industry, where the heat increases due to the high density, as well as their multitasking, and even to continue to the large-scale components in the automotive or aviation field, which need to operate at extreme weather condition and prevent such cases, as you can see here, of a plane that arrived from a flight and is covered in snow, which may damage its systems. So the second question is why we need the thermal management. What happens if we do not well dissipate the heat? So in general, thermal management is a feature controlled by thermal conductivity coefficient, and it represents the ability of material to well dissipate the heat during operation, while high thermal conductivity correlated to a better thermal management material. And if we return to the electronic industry, for example, the miniaturization and integration of them dictate the need for thermal management, again, for heat dissipation to prevent a warming. A possible solution for that is a thermally conductive polymer-based coating as an alternative to the traditional metal fins. Unfortunately, polymers have a low thermal conductivity compared to metal fins, which is epoxy, which contain 0.2 watt per meter Kelvin, while copper contain 400. Insufficient thermal management can lead to heat accumulation and consequently malfunction in the systems. Therefore, my goal is to develop a thermally conductive polymer with very high TC values for thermal management application. So in order to enhance polymer properties, we used composite materials. Composite materials are a combination of two phases, fillers and matrix, which differ in the properties. In my research, the matrix is epoxy, which is a polymer that's widely known in the industry in order to protect the devices from environmental damages. And in order to enhance its thermal behavior, I use carbon-based filler, which consider the best candidate material for TC enhancement due to their impressive TC values. They have various types of allotropes, but I used on 3D graphite flakes, defined as GF, and 2D graphene nanoplatelets, defined as GNP. They consist of multiple layers of hexagonal sp2 bonded carbon atom. Their unique structure, as well as unique thermal properties, make them the best filler for my goal, for my research goal. So before I will continue the results, I will give a brief on thermal conductivity in the world. So many studies have been conducted on thermal conductivity in the world, but I have focused only on the system that contain graphite or graphene in epoxy, since it's compatible to my research. And you can see here the thermal conductivity as function of the publication here, while each point in the graph represents the thermal conductivity in that field. Some of the paper based on the single filler system, which is the green mark, while other based on the integration of more than one filler, which defined as an hybrid, and also the blue mark. And we can see that most of the TC results are below 5 watt per meter Kelvin, while currently the highest thermal conductivity values are 11 and 8 watt per meter Kelvin for the single and hybrid filler respectively, which is fine. But if you compare between that result to the industry requirement, each industry has its own minimum TC requirement that even increase with the multiplicity and complexity of their task. Therefore, in order to achieve a significant enhancement that enables to the industry to extend the lifetime of their material and consequently a better heat dissipation, we must cross the 10 watt per meter Kelvin. So after a lot of optimization that we did, we measured the thermal conductivity and we go directly to the result. So we start with the single filler system and we measure the thermal conductivity as function of the filler concentration. In general, once we increase the filler concentration, there is increasing viscosity until a certain concentration that prevents us to load more filler. We define that concentration as the workability limit. And you can see that once we use GF, we succeeded to load more filler compared to GNP and consequently to achieve a better thermal conductivity results. Why it's happening? The possible explanation for that related to the difference in their aspect ratio. While high aspect ratio correlates to a high viscosity. And since we characterize our filler, we know that GNP have a drastically high aspect ratio compared to GF. And this is directly fit to our results. But we need to remember that in order to develop a thermally conductive polymer with impressive TC values, we need a combination of high filler loading, like GF, and the filler with impressive thermal conductivity values, like GNP. Therefore, the combination of both of them as a hybrid system seems the best option in order to cross the maximum TC results for the single filler system, which is the 10 watt per meter Kelvin at 80 weight%. So first we define a total filler concentration as a TFC for the control parameter for the total loading in the matrix. And we fix the GF concentration on 40 weight%, which is the blue column. And we gradually increase the GNP concentration, which is the red column and also the x-axis. And we tested the effect of each different column and hence different concentration on the thermal conductivity. And you can see that we obtain impressively thermal conductivity of 16 watt per meter Kelvin, a CFC of 70 weight%, only by combining the filler together. A possible explanation for the high hybrid efficiency relates to the synergistic effect between the 2D and 3D network filler, as well as increasing network density due to the difference in the sizes, which leads to a less thermal resistance and hence and consequently a better thermal behavior. But this is not the only system that we try. We did several combinations with different fixed concentration of each of the filler, as you can see in the legend. And again, we measure the thermal conductivity as function of the TFC. And you can see that once we increase the amount of the filler, there is a moderate linear increase until a certain concentration, but above it, there is a sharp change in the TC slope. We define that concentration as a thermal percolation at 50 weight%, regardless of the GF-GNP ratio. Therefore, we definitely can say that the importance of fixing one of the filler is negligible, while the ability of succeeding to load maximum filler is crucial in order to achieve a significant enhancement, such as the 16 watt per meter Kelvin for the hybrid system. Then we analyzed the microscopic 3D structure of the enhanced composite by scanning electron microscopy SEM analysis. And we found that most of our composite contains a large amount of air voids, which you can see next to the white arrow. And since air voids are a failure point in the composite, since air is thermally insulating, their appearance may affect the thermal behavior of all the composite. Therefore, in order to enhance the thermal conductivity much more, we decided to decreasing the number of air voids. It means that instead casting the composite under atmospheric pressure, we decide to pack them together by compression. So you can see here the thermal conductivity, but now as function of the different pressure at high and low filler concentration. And you can see that a non-compressed composite with initial thermal conductivity of 16 watt per meter Kelvin is enhanced to approximately 28 watt per meter Kelvin under a pressure of 250 bar, only by reducing the number of air voids. We also can see that the total for a low filler concentration, the total trend was also kept. However, in order to verify that our assumption is right, it means that the main reason for the huge enhancement is correlated to the airways reduction, we return to the same analysis, but now for the low pressure and high pressure. And you can see that for the low pressure, we still can see the appearance of the air voids, while at high pressure, they are removed and the surface is more uniform. Therefore, what we've got so far, we start with the knitted polymer with initial thermal conductivity of 0.2 watt per meter Kelvin. First, we examine the effect of the filler loading in a single and hybrid system, and we succeed to enhance the thermal conductivity to impressive TC of 16 watt per meter Kelvin. And we examine the effect of the compression, and we succeeded to multiply the thermal conductivity to extraordinary thermal TC value of 28 watt per meter Kelvin, which is very impressive. But in some application, we need high thermal conductivity and controllable electrical conductivity. For example, if we return to the electronic industry, the miniaturization and integration of them dictate the need for thermal management for heat dissipation, but they need also a controllable electrical conductivity to prevent a short circuiting. Therefore, we need to develop a thermally conductive polymer with controllable electrical conductivity. Unfortunately, the fillers that we use so far, which are carbon-based material, are characterized by both high thermal and electrical conductivity. Therefore, the combination of the boron nitride as a thermally conductive with electrical insulating seems the best option to receive the desired properties, which are high thermal conductivity and also controllable electrical conductivity. So the system that produced the best results is the GF with the boron nitride as a fixed boron nitride concentration on 38%. And again,
sorry, we measure the 3 minutes left. I'm sorry for interrupting. Bye-bye.
Fine. We measure the thermal conductivity and the electrical conductivity as function of the GF addition. When you can see that we start with a ceramic-based filler, which characterized by a moderate thermal conductivity, but very low electrical conductivity. And you can see that once we increase the GF concentration, we sharply increase the thermal conductivity, but unfortunately, we also increase the electrical conductivity. Therefore, we want to examine the effect of the compression on the controllable system. So we took the composite that contained TFC of 65 weight %, and you can see that under pressure of only 25 bar, we succeed to enhance the thermal conductivity to 12 watt per meter Kelvin compared to only 5 before, and reduce the electrical conductivity at 2 orders of magnitude, which is very impressive. So if I conclude my second research goal, we start with a ceramic-based composite, which characterized by a moderate thermal conductivity with electrical insulating. First, we examine the effect of the carbon loading, and we succeed to multiply the thermal conductivity, but also increase the electrical conductivity. And finally, we examine the effects of the compression, and we succeed to drastically enhance the thermal conductivity with controllable electrical conductivity. So if I conclude my entire work, we definitely can say that compression enhances the thermal conductivity and also control the electrical conductivity, which can be proved by the same analysis. And if we put our best results in the world, we achieve the most significant enhancement in that field. This is only some part from my work. For further information, you can scan the QR code for the full paper, which published on carbon. I would like to thank my supervisor, Professor Oren Regev, my group member, and of course, you for your attention.
So great talk. I enjoyed it really much. Does anybody have any questions?
Yeah, can I ask a question?
Yes, Maxim, please.
So first of all, thank you, Avia, for the very interesting talk. I think in slide 8, you showed a graph where you showed different ratios of GNP and graphite, and they had the same thermal conductivity behavior regardless of their ratio between them. Can you maybe give a reason why? Like maybe say, yeah, this one.
Okay, here?
Yeah, why doesn't the concentration, the percolation concentration, why doesn't it depend on the ratio between the GNP and the
Since
graphite?
the both okay, this assuming is relevant only for carbon-based materials, since we know that the GNP and GF are characterized by both within similar thermal properties. Therefore, the combination of both don't have a minor effect on the entire behavior, only on the ability of succeed to load more filler. For example, if we were succeeded to load to use only GNP, which is the carbon-based filler that characterized by the highest thermal conductivity, and we succeed to load more than 45 weight percent, as I mentioned in the beginning, probably we may able to get a higher thermal conductivity compared to GF. While the main problem once we use the GNP is only the low loading, the high, yes.
Yeah, but for instance, if you use only GNP, you say that you expect to see the same thermal conductivity behavior. After 45%, you would expect to see also a change in slope because of percolation.
Yes, but the percolation, it comes at 50 weight percent, that's we found. And once we use GNP, we succeed to load low filler compared to 50. So we assume that if we was able to cross the 50, probably we also can see that.
Yeah, thank you.
So I have a question, which I'm not sure of. You're using huge amounts of weight percent, like your weight percentage is very large. So I wanted to ask, did you test, or is it even relevant to the application, the effect of such a high weight percent on the mechanical strength of the final product?
Probably, as Gal Michaeli Shachar say in the beginning of the session, yeah, once we increase the amount of the filler, probably there is a reduction in the mechanical properties. The purpose of my research was to enhance the thermal conductivity high as possible without taking into account the mechanical aspect.
Okay.
Okay.
Okay. But what? Okay, and
there are a lot of applications that the viscosity as well as the mechanical properties, it doesn't matter to them, since they are casting the composite. It means that they need that the material will be a powder or a viscous in order to enable their application. For example, the thermal interface material or the EMI electromagnetic interface shielding, it's fine. But of course, there are a lot of other applications that probably the mechanical problems which may be a problem in that case. Yes, you're right.
Okay, and I have one more question, but I heard someone say something. No, so I will ask the question. In your thermal pressure, when you apply the pressure, could you move to the slide?
Mm-hmm. Yes.
Yeah, so I'm guessing it's maybe like IP or something like that, but what is the process of applying the compression? Is it just it's slow compression? It's not, I'm guessing it's not instantaneous.
In the beginning, we took the filler and the matrix together, mixing them in our special technique with the Thinky ice shear mixer. After we ensure that the fillers are homogeneously dispersed in the matrix, we directly go to the hydraulic press at room temperature, and we only and we press it under different pressure from 25
So
to
you're,
250.
and you said you're using atmospheric air, not like
Yes,
inert
not,
atmosphere.
yes, we didn't change the room temperature.
Mm-hmm. The room temperature, but in air, not like
Yes, yes,
inert.
yes.
Good.
Mm-hmm.
Okay. Thank you very much. Good
Thank
luck
you.
in your in your future.
Thank you very much.
Bye bye. I'm finishing our session.